The recent high-profile announcements made by NVIDIA, Siemens, Pepsi, and others across manufacturing made one thing clear. Digital twins and AI are no longer experiments. They're becoming the operating model for modern production at scale. But for most manufacturers, the challenge isn't believing in the future. It's getting there without disruption, without AI theatre, and without losing control of data and IP. At TCOM Corporation, doing business as TAAIB, we built the TAAIB vCPPS platform to unify what's usually fragmented. Full-line digital twins, no-code PLC logic, behavior profiles, and a governed intelligence layer. This spring, we're opening a rare opportunity. Near-zero-cost pilots supported by Georgia Tech Senior Capstone students' work, so forward-looking manufacturers can experience real physical AI outcomes on real lines, not dashboards. Before we go further, it's important to understand that the TAAIB vCPPS platform is a full-stack operating framework made up of multiple layers that span the plant's virtual commissioning, simulation, control logic, and data foundation. But in this presentation, we are intentionally focusing on one layer in particular, the TAAIB vCPPS platform intelligence layer. Because this is where physical AI becomes real, and where manufacturers either gain operational advantage or get stuck in disconnected analytics. What you're looking at is an integrated system, because manufacturing doesn't run in pieces. The AAS digital twin gives the plant a living structure: assets, process areas, sensors, actuators, and constraints. Descriptive AI and ML turn operational data into signals, trends, anomalies, forecasts, and maintenance risk. And then the key: governed agentic GenAI, an AI assistant that doesn't guess, but operates through stage gates, evidence retrieval, and enforcement. And tying it together is optimization. Grasp plus reinforcement learning. So the system doesn't just explain what happened, it learns the best actions under real constraints. The pilot is designed to be lightweight for your team. You provide limited SME guidance. We do the heavy lifting. Then validate everything against operational reality.
Every successful intelligence layer starts the same way: scope before answers. Here, the GenAI module begins by grounding the request in the plant reality: which line, which time window, and what goal. That sounds simple, but it's the difference between a chatbot and an industrial-grade assistant. This scoping step ensures the system only uses the right assets, the right data window, and the right constraints, so downstream recommendations are traceable, auditable, and tied to the actual production context. Next, the system explicitly asks for constraints, because in manufacturing, the best action is meaningless if it violates quality limits, safety rules, or operating envelopes. This is where the assistant aligns to your behavior profiles, BPs, and advanced machine behavior profiles, AMBPs, the rules that define what sensors and actuators are allowed to do under different conditions. This is also where deterministic manufacturing discipline meets probabilistic AI. The AI doesn't improvise. It commits to working inside your operational physics. Now we enter the plan evidence phase, and this is one of the most important moments in the entire workflow, because this is where the AI assistant commits to how it will prove what it's about to say. In manufacturing, you don't want opinions. You want answers that are grounded in the plant and defensible to operations, maintenance, and controls. That's why the platform builds an evidence plan across 4 sources. First is asset context, pulled from the digital twin using AAS, which stands for Asset Administration Shell. Think of AAS as the plant's digital index card system. It tells the system exactly what equipment exists, how it's connected, what sensors and actuators belong to each machine, what limits apply, and what operating rules exist. Second is telemetry and event data. That's the time series sensor readings and the operational events. Starts, stops, alarms, jams, quality rejects, changeovers, everything that describes what actually happened on the line. Third is descriptive model outputs. Descriptive AI is the layer that turns raw plant data into meaningful signals like, this behavior is abnormal, this asset is drifting, this subsystem is trending toward failure, or this process window is tightening. It's not guessing. It's pattern recognition based on your data and your physics. And then we bring in a fourth source that is unique in most manufacturing AI approaches: GRASP plus RL Insights. GRASP stands for Greedy Randomized Adaptive Search Procedure. In plain terms, GRASP is a powerful way to search through many possible explanations or decisions and quickly find good candidates without needing perfect information. In manufacturing, that matters because there are often many interacting variables: temperature, moisture, feed rates, RPMs, pressures, timings. And the best solution is rarely obvious. GRASP helps us identify the most meaningful combinations of factors and the most promising options to test first. RL stands for reinforcement learning, which you can think of as learning by trying. But in our case, trying inside a virtualized production system, not by experimenting on your live line. RL learns which actions tend to improve outcomes, like throughput, quality, or energy efficiency, while respecting constraints. Here's the key. GRASP and RL live upstream in the intelligence layer as part of descriptive AI and optimization, and they feed the GenAI assistant with disciplined, structured insights. That means when the GenAI module later produces recommendations, it's not just generating text, it is assembling guidance that is backed by the plant structure, AAS, what the sensors and events show, what the descriptive models detected, and what the optimization layer learned is effective under constraints. This is exactly how we make probabilistic AI behave safely in a deterministic environment. We plan the evidence, gather it, validate it, and only then do we allow the assistant to recommend actions. Here's where the platform behaves like a real industrial system. It pulls evidence from the digital twin structure and the data layer, and it stamps each retrieval with traceable references, so every downstream insight can be audited. This matters for pilots too, because our deployment is intentionally designed as creep, walk, run. In the creep phase, we start in our private cloud to move fast, stand up the digital twin, simulate the data sources, and prove value with minimal friction. In the walk phase, while still set up in our private cloud, we begin to layer on your plant's historical data, structured and unstructured, to close the gap between the established virtual environment and your real-world operations. However, by the time we reach the run phase, we bring the capability to the plant as a plant-owned mini data center / near-edge stack that runs the intelligence layer close to operations. That shift changes everything. Privacy and proprietary information stay under the plant's control, and latency is less of a concern, as the data center is within your plant, allowing data movement, communications, and decision-making within the plant to be much faster, which strengthens the value proposition. In other words, we don't just show you results, we give you a realistic path to operationalizing them on-site, securely, and at production speed.
Now the assistant summarizes and analyzes, turning raw evidence into operational understanding. It highlights what changed, where it changed, and how it connects. Throughput shifts, sensor drift, event patterns, anomaly detection results, and regime changes identified by grasp and reinforcement learning. Here's how it does that in a way manufacturing teams can trust. First, it uses the digital twin structure to anchor everything to the real plant. Process areas, machines, sensors, actuators, SKUs, and known constraints. That prevents the system from mixing signals across the wrong assets or pulling the wrong context. Second, it takes the raw telemetry and events and converts them into engineering summaries, things like deltas, trends, spikes, stability bands, and timing correlations. For example, throughput dropped immediately after a changeover, or moisture drift increased before jams began. Third, it overlays the outputs from the descriptive models, so you're not just looking at data, you're seeing what the models detected. Anomalies, degradation signatures, risk scores, and forecasted outcomes. Then comes the piece that separates this from typical analytics. The system uses GRASP plus RL artifacts to interpret behavior under constraints. In simple terms, it identifies which operating mode the line is in, stable, drifting, stressed, or unstable, and what combinations of variables tend to push the system into those modes. That gives you a structured explanation like, while producing SKU3, this line entered a stress regime when fill rate and moisture crossed a threshold, which increased downstream jam probability. The result is a single coherent operational story, grounded in evidence, so engineers and operators can quickly validate what they're seeing and decide what to do next. This is where the value becomes tangible. The system produces recommendations as structured options, each with clear benefits, risks, and trade-offs. It doesn't pretend there's one magic lever. It offers multiple paths aligned to your goals: throughput, quality, energy, and uptime. And it ties each option back to the evidence and constraints of the actual line. What makes this different from most agentic AI in manufacturing is not that we use an LLM. It's that we wrap the LLM inside a 7-module orchestration layer designed for deterministic operations. First, buckets maintain a controlled, auditable session for the job, so the system never loses context or mixes state. Second, the director acts like a plant-grade workflow controller, deciding what must happen next and preventing the assistant from jumping straight to conclusions. Third, the booster packages the right plant evidence, digital twin context, telemetry summaries, descriptive AI outputs, and GRASP plus RL insights, into a form the model can reason over reliably. Fourth, helpers are the tool layer that retrieves facts from the plant model and data streams, while fifth, helpers utilities standardizes IDs, validates structures, and keeps every output consistent and checkable. Then the 2 modules manufacturers care about most: enforcement and story game. Sixth, enforcement is the gatekeeper. It ensures every recommendation stays within safety bounds, quality limits, actuator constraints, and BP/AMBP rules, and it refuses or repairs any output that doesn't comply. Seventh, story game is how the system stays usable on the plant floor. It guides the interaction, asks only the minimum clarifying questions, and keeps the narrative aligned to operational reality, so engineers and operators can trust it. The result, from these 7 integrated agentic layer modules, is that the recommendations you see here aren't just AI text. They're the product of an industrial-grade orchestration process that is evidence-driven, constraint-aware, and designed to transition safely into validated draft logic templates. This is the gate that manufacturers care about most: enforcement and validation. The platform checks role permissions, validates alignment to the digital twin context, verifies safety and actuator bounds, runs simulation pre-checks, and confirms output conformance. So what moves forward is not AI text, but a controlled, reviewable artifact. This step is also where the TAAIB vCPPS platform approach clearly differentiates. Many market approaches, like the NVIDIA, Siemens, Pepsi style roadmap, are powerful at scale, but they often emphasize broad transformation, infrastructure, and enterprise standardization. TAAIB vCPPS platform is built operations first. The goal is to make AI usable where decisions actually happen, on the plant floor, by converting recommendations into validated templates that respect BP/AMBP, PLC realities, and local constraints. Operationally, that means we don't rely on trust in the model. We rely on proof through enforcement. Evidence must exist, constraints must be satisfied, simulation checks must pass, and the output must be audit-ready before anything is allowed to proceed. Only after clearing this validation gate does the workflow allow the next step, generating a draft PLC logic template, so manufacturers can adopt physical AI through a disciplined creep, walk, run path, without letting the initiative drift into the category of AI projects that never make it to operations.
Finally, publish. Generative AI deployment done the right way. The TAAIB-vCPPS platform. Intelligence layer generative AI output is not a free-form command. It's a structured, validated logic template with rollback and refinement paths. This is the moment where pilot participants see the difference. We are not producing AI text. We are producing a governed artifact that fits into industrial workflows. For a pilot, in adopting our creep, walk, run deployment approach, this is where the business value shows up. Faster diagnosis, safer optimization, fewer unplanned stops, and a clear path from analysis to action without disrupting production. If your organization is exploring digital twins, AI in manufacturing, or how to move beyond pilots into production-ready physical AI, this is your opportunity to be early, not late. As you look at this TAAIB vCPPS platform intelligence layer, here is the point we want to leave you with. Physical AI in manufacturing will not be won by dashboards, one-off pilots, or disconnected analytics. It will be won by the manufacturers who can operationalize intelligence, line by line, process area by process area, grounded in real plant physics, real constraints, and real operator know-how. That's where the TAAIB vCPPS platform is fundamentally different. The NVIDIA, Siemens, Pepsi model is powerful, but it is also heavyweight, often optimized for organizations that can afford massive integration programs and long transformation cycles. TAAIB vCPPS platform is built for operations-first deployment. Full-line digital twins, no-code PLC logic, behavior profiles, and a governed generative AI assistant that doesn't just talk, but works through evidence, validation, and safe templates. Most importantly, it is designed to capture and codify tacit operator knowledge, the unwritten rules, the practical thresholds, the judgment calls, so that expertise becomes a scalable, auditable asset that benefits the entire organization, not just the best shift supervisor on the best day. And we're not asking you to bet the plant on AI. This pilot is deliberately structured as creep, walk, run, a low-friction entry that de-risks the journey, proves value quickly, and prevents your initiative from becoming part of the 95% of AI projects that never truly get started. If you're a discrete or continuous manufacturer, or even an energy generator, this is an opportunity to participate early, at near zero cost, with real technical support, and emerge with a validated digital twin and an intelligence layer that is designed to move from insight to action safely. If you want to lead rather than follow, reach out to us at TAAIBMaccorporation.com. Let's build your pilot on the plant floor.